Hello. The webinar again about object-oriented programming. And this time, let me check the audio. Yeah, and this time we'll talk about thread safety. It's going to be quite high level, if I can say, introduction to thread safety in Java, which I think most of you understand quite well. So if you are a professional, if you are a seasoned Java developer, then maybe this webinar is not going to be for you. If you are just starting, if you are still learning like I am, then maybe we'll be able to learn something together. Well, I'll share you what I have. So thread safety. Let me make my face smaller. Well, first of all, let me. That's what I wanted to do. I wanted I want to say what it is in general, thread safety, because for me, for example, many years ago, I was quite surprised when I moved from single-thread languages or environments to multi-thread languages and environments. Then I was surprised that many paradigms, many concepts were actually new for me. So a single thread means that the CPU means that all objects and all variables and all data elements which you manipulate, they exist and they can be managed or can be modified only by the instructions which you see in front of you. So if you say that the object X must be equal to number 1, then it is going to be equal to number 1 right here now until you change it somewhere later in other instructions. This is called single thread environment. So nobody touches your other variables from nowhere. So you're 100% sure this is only your variable X, which you can only access and only you can modify it. So if it's going to be, if you set it 1, it's going to be 1, many instructions later if you don't change it. Multi-threaded environment is something different, which means that you create an object X and you may give access to this object X to another thread, so-called. So you can call it a thread, you can call it a process, you can call it a execution flow, you can call it there could be other names, but the concept is that another set of instructions, another flow of instructions, another directives may change your object. So if you say X equals to 1 and then you have another 5, 10, 12 instructions, then it doesn't mean that after these 12 instructions it's going to be still 1, because some other thread which is running in parallel to your main thread, to the thread you're looking at right now, it may change your variable. So it basically means that there is one place for data and many places for code. So the data, they stay together in one place, and they are so-called shared data. So we share that objects and variables and just data elements, memory elements. And there are multiple pieces of code which run in parallel. If it's one computer, one central processor unit, one CPU, then usually this multi-threading is implemented by switching context, so-called. So like imagine like the first second we give time to the first thread. And then we ask the CPU to take a pause and switch to the second thread and move it forward a little bit. And then the second number 3, we ask it to pause and switch to thread number 3. And then get back to thread number 1. So every second we switch from one thread to another. Every second or every millisecond or every nanosecond, it depends on the situation. But this is what happens in one CPU. If there are multiple CPUs, like in modern computers now, we have 8, 16, whatever, 64, a million, doesn't matter, CPUs. So then we give one thread, we give to one CPU, and then another thread we give to the second CPU, and then so forth. So each computer moves forward, each CPU moves forward on its own. But they all have access to the same data set, to the same territory of data. This is what happens in one application which is multi-threaded. Of course, if you start another application, then inside that application is going to be a different territory, different area for the memory, and then there will be different processes, different thread, everything will be different. But in one application, the core idea of multi-threading is that we have centralized place for data and multiple copies, not necessarily copies, they could be different, but multiple threads which are doing something in parallel. Why do we need that? What's the point of that? The main point is that we want our application to move forward faster than with one thread. Why? Because multiple threads helps us to solve the situations of well, there are basically two reasons. The first one is that we have multiple CPUs. So let's say they give us the computer and there are 4 CPUs inside. So if our application is, let's say, calculating the some numbers or running some algorithm, then it's going to do it in one CPU, and all other 3 CPUs will just stay and wait, just doing nothing. So we're not going to use the full resource, the full capacity of the computer which we have in our hands if we just run it in one thread. So we want to keep other 3 CPUs busy as well. So that's why we need multi-threading. That's one reason. But the second reason, even if we have one CPU, still multi-threading makes sense because quite often we need to wait for some external event. Let's say I send a request, an HTTP request to another server, and then the server replies, and I process the reply, so I do something with the reply. Between these 2 moments of me sending the request and me getting the response, there could be like a few seconds, or maybe, I don't know, a few milliseconds, but usually it's going to be like a few seconds. And during this time, we'll be staying and waiting for the answer, which is not effective use of the CPU, because the computer, if it's going to be one thread, the computer will be locked, and it will not be able to do anything. It will just, the application will be locked and will just wait for the response from the server. In some situations it's okay, but in most cases we don't want to do that. We want to continue and do something else, and that's why we need to sort of parallel our executions. We need multiple threads. Another example, well, real practical example, is a web server. So it's a really, that's the place where I use multi-threading all the time, and everybody do that. Everybody does that. It's a server which is staying and waiting for the request from the user, HTTP server, and then when request arrives, then we start preparing some answer to give an answer to the user, to the HTTP client, to the browser, for example. But then another client comes in, another browser opens up the page and wants something from us. So we don't want the second client to wait for the first one. We want them to be served simultaneously. And that's why we need multiple threads. We need to, every time the new client comes in, we create a new thread and then let the computer run everything and return the data back. And then at the same time, we create a second thread, a third thread, and many, many threads. That's why modern web servers, they are multi-threaded applications. You can't do it in one thread. That will be too slow. So you need some solution for making it parallel. So that's the bottom line. We can go. We don't want to go deeper because there are solutions for web servers on a single thread. It is possible to go around this multi-threading problem and implement it differently. But it's not the point of this webinar. The point is that we need multi-threads. We need them to go in parallel. And the problem is now what to do with the data, with our objects. So if we have one object, let's say it's a web server, and I have a container of data or an object which represents the data, and there are multiple clients coming in, multiple threads are trying to touch that object at the same time. So we need to be careful, and that's the point of this discussion. We need to be thread safety, and I'll explain now what it is. Let me make my face smaller, and I'll show you what I mean by thread safety by real example. So here's the code which I wanted to show you. We'll do some live coding today. So let's start with a very simple object. Let's call it users, which is going to be, let's say, a container of users, which they will have, let's say, balances. It's going to be a bank account. You know, we'll keep the, you know, let's call it bank. So we have a bank, and we have, let's say, our balances. Okay. It's just a primitive hash map of balances. 0 in the beginning, and then we say we want to add some money to the user. We say the username and how much dollars we want to put on the balance. We just increment or decrement. What we do here is that we say this balances. First of all, we do it like this. User, if there is nothing, then we put 0, no balance, and then we say this balances get user. I guess that's the way it should be. It's rather primitive, but it's okay for our, you know, for our conversation. That's it. And now let's run the test and see whether this code works. So I say bank, new bank. And then I say bank. Oops, why it's balances? We want to add, create user here. It's going to be me. Add $5. Okay. And let's make it, you know, even better. So every time we add something, it returns the final balance of the user. I know it's not really a good, you know, good practice, but let's do it this way. So what I want to do is I want to assert, I'm using Hamcrest, I want to assert that after I add it, it's going to be 5. Assert that 5 equals to 5. Let's run it and see if it works. I hope it will work. I'm staying inside Cactus framework because we're going to use a few simple primitives from this network. I'm not promoting it now. You can see other webinars for it. Now the main point is to talk about thread safety. And there will be maybe some examples I'll show you from this library of synchronized decorators, which is the final point of this webinar. So I'll try to explain you the problem and then show you a few solutions. And in the end, we'll see how these synchronized decorators may help us. You see, so it works now. Everything is clean and it's good. The problem will show up if this bank will be accessed. Let's make it nicer. If this bank, then somebody else will. Let's try again. Let's add another 10 and the balance is going to be 15, right? Let's run again. I don't know why it takes so long because of the video probably. Yeah, so it works again. You see, so I consequentially incremented the balance 2 times and it is 15 in the end. So everything is clear. So far so good. But here comes the problem of multi-threading. So now we have just one thread. Like I told you, this is just a set of instructions. They go one by one. Here's the memory space. We cannot call an object a memory space, but it is technically behind this object bank. There is some memory space, which is now accessible by just one thread. And now I'm going to create a second thread here. How to do it in Java? There is an object called thread, and I provide a runnable inside, which can do something, and I call it thread. Let's call it thread. And then I do thread start, and then I say thread join. Join means that, I'll explain now what it is. Since we're in Java 8, we can simplify this code, and here I say like this. Yeah, and here let's add 20, and in the end I think we will have 5, 10, 20. So we will have, I believe, 35. So what happens here? See, we can even simplify it further like that. So in the main thread, in the main execution flow, we can't call it main or not main. These threads are they're mostly equal. There are two types of threads in Java. There are daemon threads and non-daemon threads. But for this situation, they're equal. It's not important, daemon or non-daemon, because they both go in parallel. So what happens here? We create an object, which is an object, and then in the main thread, in the primary thread, and the first thread, that's the name. In the first thread, we increment it by 5, and then we create a parallel thread. So let's imagine we have a second CPU, a second processing unit, and then we give this CPU a different set of instructions. This is the set of instructions for the second CPU, and then we are saying start it. So we are the first thread is giving instructions to the second one. So the first thread is still here. It just created the second one, and then it gives instructions to the second one, like start it, go forward, execute the instructions you have inside. And then here we wait for it to finish. So this second thread which we created, it will execute the instructions, it will increment the bank account by 10, and then it will finish here. And then we will increment the balance by 20, and we will get 35. So actually what will happen is, imagine the execution of the first thread, and then the second one, and then the third one. So they will go consequently, not in parallel technically, because first these 3 lines will be executed, then these 2 lines, these 3 lines will be executed because we say so. Then we say join, so we're going to wait for them to finish. They will make sure that the second thread is finished, and then we get back here. So here actually the first CPU will wait for the second one to finish. So if you put on the graph, then this one goes the first thread, and then the second one, and then the third one. They don't go in parallel. Let's run it, and we will see that this result will be 35. I'm sure that everything will be clear now. If you follow, yeah, you see, it's okay, it's good. There are no conflicts because there are no conflicts. What it may go wrong if I move this line here. I guess you understand why. Because here's what's going to happen. This is the first thread. It makes an object, and it runs something. It adds a number to the object, and then it creates a second thread. It says go forward. It starts to work. It starts to add something to the bank, and we immediately start to do the same or the different operations in the primary thread, in the first one. And here in this line, they will go in parallel. They may clash. They may have conflicts because they will at the same time will try to do something with the bank, try to modify some balances of the user in the bank. So maybe we may have a problem here. Let's run it. Maybe not, because it's something which is not predictable. This is one of the biggest problem of multi-threading, biggest problem of this thread safety problem, is that kind of bugs or troubles are quite unpredictable. Let's see. Maybe it will go fine now, maybe not. Boom. You see? He failed. On the first run, it says 25 instead of 35. Let's run it again. Maybe it will work. It doesn't work again. Let's try again. There's no guarantee, so you don't know. It's, in some situations it may work. Maybe I'll run it for 100 times. It will always fail. I don't know. You see? Now it works. So that's the problem of multi-threaded environment, because you never know what's going to happen if two parallel threads of 5 or 10 or how many will manipulate with the object in parallel, and the object is not thread safe. Here comes the point. So this object is not thread safe, and now let's see why it's not thread safe. So what's going on? Why we fail? Why these two parallel threads are trying to do quite simple manipulations with the data, and if they do it at the same time, if they try to do it at the same time, they fail. So look at what's happening inside an object. We have this hash map of balances, which is quite primitive associative array. Here we put the number 0 if the user doesn't exist. Then we take the balance out of the hash map. Then we increment it by the number, and then we put it back to the storage, and then we return what's left. So the problem comes here. Look, let's break it down into parts. Let's say I'm just I'm doing it in order to demonstrate. So here's the balance. This is what happens actually. We can of course compress it down to one liner, but technically this is how it works. So first of all, we take out the balance of the user, which was the balance before. Then we increment that balance, and then we put the incremented number back to the storage. If nobody is touching this storage, this array of users and numbers, if nothing happens here between these three lines, then everything is fine. But imagine that we are doing these operations from two different places, from two different threads, and then here this before. Let's say I want to increment it by 10 and I want to increment it by 20. So the first thread is doing this, and then let's call it this one. And this is going to be, the first thread will get this value, and the second thread will also get the same value. And then both of them will do this. Right? And then they will do this. So what's going to happen? Look at this. If this is 10 and this is 20, then still the result will be here. So the number which we save here will be ignored, because we're going to simply override it on the second line. Do you follow? Take a look again. The first thread will get the number. The second thread will get exactly the same number. If the balance was 5 before, then they both will get number 5. Then they both will increment it by different numbers, by 10 or by 20. So the first thread will get 15, the second one will get 25. And then they will both try to save their results to the storage. The first one will save 15, the second one will override it with 25. So we're going to lose the calculation, the result of the calculation of the one of them. We don't know which one, first thread, second thread. We may lose the result. So this class, if this is what happens inside a class, it's called, people sometimes, we do it in our documentation, we say this class is not thread safe. So this term means that you cannot use it in multiple threads. It's going to fail. Maybe not. But there is a possibility that this situation, this it's called race condition. So it's like a problem. Imagine you have like horses are racing, and they're moving forward. You don't know which one is in front of which horse, and because of that, if the first thread is ahead, then the first thread will win. If the second thread is ahead, then the second thread will win. So we know what's going to be the order of these lines. Maybe this one, maybe that one. And imagine what will happen if we have 15 threads. If there are 15 clients coming from the HTTP, front end, and all of them are trying to change the balance of the same user. So it's going to be 15 different requests for changing the balance. We don't know who's going to win one of them. And in this situation, so we don't know who's going to win. That's the problem. It's called race condition. Yeah, I think that's the term. So what do we do? How to solve that? How to make this class thread safety? Let's get back to the right code. Well, there are a number of solutions. The first one, which I think is the right one, is to say that it's not thread safe and call it a day. So it is not thread safe, don't use it. If you want to use it, then you need to create some decorator on top of that. So, but I will explain you now what it means. First of all, let's see how we can make it thread safe. What's the technical solution? For those of you who doesn't know how it works, if you see this line in the documentation, you should know what it technically means. It technically means that this class inside has the manipulations which are not atomic, so-called. So this set of instructions, the set of instructions is not atomic. So it means that it cannot be treated as a single operation. I think that's that's my interpretation for the word atomic. Atomic. Yeah. So we can call them atomic. So this line is atomic because it will always execute it as it will always run as a single instruction. It will never break into parts. It doesn't have parts inside. It's always one. So it either fails or returns what's asked. It either works as a whole or it doesn't work at all. This set of lines is not atomic because they may, like we saw before, they may deliver different results if we inject some changes, some parallel situations on the background. So it's not atomic. How to make it atomic? We need to make it atomic to make it thread safe. That's I think is the only way to make it thread safe. So we need to guarantee somehow that when we start here and then we finish here, we need to have a guarantee that nobody will touch my storage of data when I'm going through these lines, through these 4 lines. How can I do that? Java gives us the native instrument for that. We need to say synchronized like this. I'll explain you what it means now, and like that. So this synchronized word means exactly what I just said. It means that everything that stays between these two curly brackets, all these lines, when we start here, all other threads which will try to also do the same, they will be locked and they will stay and wait until we finish. That's what it means. So basically, the Java machine will put them all on pause and ask them to wait until we finish. We finish here, and some of them will be able to do this. Will be able to execute these lines. And then the next one will finish. The third one will try again. So now this code will work 100% because of the thanks to this synchronized word. Let's run it. Let's run it and see. It's 100% guaranteed. It will always be green, no matter how many times I run it. But of course, you understand it that now we don't have the parallel execution. We have synchron. What? Maybe this one. I don't think so. That's interesting. Funny. Let me check the chat. What do you guys think? What's going on? Do you know what's going on? Yeah, I moved my face, sorry. So why doesn't it work with the synchronized word? Any ideas? Nobody knows. Okay, let me check. Yeah, there's a suggestion maybe. I don't think that will help, but no, it's not about that. Oh, that's right. Yeah, that's right. Yeah, that's a right comment. So this line is checking the balance when this thread is still running. Well, this thread is still calculating what's going on. So that's right. So we need to the assert is wrong. So okay, my fault. So we put it like this: assert, sorry, 0, so it doesn't modify anything, and we check that it's 35. And here I go. Yeah, sorry guys. So let me get back again. So I say 20 here, and I say 10 here, because of course we cannot assert that what's going to happen on each particular line. So this is correct. So we add 5, then I add 10, then I add 20, and then I join, and then all the threads are done, and then I add 0, and then it should be 35. So it should be 5, 10, and 20. And the result should be 35. That's correct. So let's remove the synchronization and run it again. So I have to see the error. There should be a problem sometimes. It works. Don't tell me it's going to work always. Let me try again. If it will work always, okay, I'll do something else. We have, maybe it's a good time good moment to show what we have in Cactus. We have an object which is called run in threads. Yeah, let's run in multiple threads. There is something in Java which is called executors, and let's do this operation for 10, not just once, because it's maybe not enough, so we don't see the real parallel execution. Let's do it 100 times. So let's create 100 threads which will go in parallel, and all of them will try to increment the balance of the same user by 10, and then see how it behaves. So we don't want to create like 100 thread objects. Let's use executors. It works like that. We have executor service. Let's create a thread pool of 100. So this one will create a pool of 100 threads ready to start, and then I will and then I will ask that pool to execute the same it's called submit. Here. I don't need that. Okay, so I submitted to the thread. So what happens here is that I have 100 threads waiting for me, and then I run a cycle and I do 100 times the same piece of code. I submit to this pool, and the pool will execute them all the moment I submit it. And then I want to wait for the service to shut down. So I want to make sure that all that threads are finished, and I do it. Well, we can do it in await termination. So I say let's wait for 1 minute. That will be too much. For 1 second to finish them all. So this await termination will wait for 1 second, and if all of them are finished, then it will return true. So let's assert that it's true. So what happens here? We create a pool of 100 threads. They're all staying, waiting, doing nothing. Then we submit the same piece of code to all of them, and they run that piece of code immediately here. And then we wait for them to finish, because I don't have 100 CPUs, so they will share the same CPUs, and they may take some time before all of them finish. And then here I wait for them. I don't want to jump to this assertion, to this assert immediately. I want all of them to finish, and I want to make sure that they are done and the balance of of the user is correct. So if I start with the balance 5, and then here I do 110, so it means 105, right? So if I add 0 here, it has to be 105. That's approximately, it's not really a good example of the multi-threading testing. I'll show you why. But for now, we just want to see the error. Yeah, the assertion. Okay, the assertion error means that probably 1 second is not enough. Okay, I'll give it 10 seconds. I guess it was the timing. Oh no, we need to shut it down, sorry. Jesus, I'm too tired. Yeah, I have to say service shutdown. So I'm saying shutdown, it means that finish all the running threads and close. Okay, it works. It works. Let's run it again. Okay, it works. I think the problem here, why it works, we want to see the failure. We want to see how it fails. So we want to see how this, how this not thread safe object actually fails. In order to see that, I think what happens here is that when I say submit and I give this code, then before I jump to the next cycle of the loop, this code is already finished. So actually what happens here is that these 100 execution pieces of instructions, they go one by one, not in parallel, because the computer is quite fast. So when I say submit, then it just immediately increments the balance of the user, and when I come back with the new submit, the balance is already updated. So we don't already go in parallel. To get rid of that, to fix that situation, it is recommended to use so-called countdown latch. So let me show what it is. Countdown latch. Countdown latch 1. This countdown latch is kind of a sort of a lock, sort of a trigger, which is set to number 1, and then here we say latch await. So this line means that we're gonna wait for this latch to become 0. So we will get to this next line only when the latch is 0, which is not gonna happen when we just run submit 100 times. So we will submit our code to all 100 threads. They will all start and none of them will finish. They will all be stuck at this line because the latch equals to 1. And they will all be stuck here, staying there and waiting. So imagine there are going to be 100 threads staying and waiting for the latch to become 0. And then here we say latch countdown. So first of all, we create a pool of threads, we give them instructions, they get stuck, they wait, they set on hold, and then we drop the latch and all of them start to execute. So now all of them will do this bank add simultaneously. So now I am 99.9% sure that we will have the problem. We will have the synchronization issue. If it's not going to happen, Jesus. Okay, let's try again. Maybe we need 1,000 threads. Yeah, it goes quite fast. Okay, let's increase the number. We want to see how this how this object is not thread safe. Yeah, finally. So for 1,000 threads we fail. You see the number is not, oh sorry, it has to be for 1,000 we need 10,005. Yeah, there you go. So it has to be this number. Look. But we don't hit the number, so sometimes we will see the concurrency issue. See, boom, we needed 10,005, we got 800,535. Let's run again. You see, every time the number is different. Each time we get unpredictable result. It's unpredictable. We don't know when exactly we're going to fail. You see, we always miss something. We always going to get a number which is smaller than the number which we're looking for. And every time it's going to be a different number. And you see how interesting. This problem manifests itself only when the number of threads is quite high. So imagine 1,000 threads on quite a small computer. I have just 8 CPUs or so. Yeah, I guess 8. So we need a really big amount of threads. That's because the code is quite primitive. So this code in the object is quite simple here. That's why we need a really big amount of threads to see the problem. And now let's put the synchronized word. I still want to show you, to prove my point. So here comes the synchronized word, and let's run it again. So now, again, I'm 99.9 sure that now we're going to get the right number. See? For 1,000 threads, we get the right number. Let's run we can run it again. We'll get another success. That's how it works. So now we actually ask the Java machine to make sure that when these lines are running, and let me put this line outside of the brackets. This is how it should be, because this one is atomic. We don't need to put it, we don't need to lock the object when we're doing this. We only want to, and here, look, this put if absent. Yeah, let's run now, and I'll show you. We'll discuss this line. See, it's still okay, because this line is atomic. It's safe, because we're not modifying anything. We're just getting. So it's always, getting, retrieving, reading data. It's always thread safe. You can read the data in as many parallel threads as you want. You're not going to damage anything, because it's reading. You're not modifying anything. The actual modifications are happening in these lines, in these 4 lines. Here we modify. We put there 0 if it's absent, and we modify here. So what about this line? Maybe we'll discuss it in the end. But here comes the point. The question is, what do we do in object-oriented programming when we have objects which are not, which are just objects, and they're not supposed to be, thread safe. So let's say we have this object. We just designed it. We never thought about, we were never thinking about thread safety, and this is our code. It looks good, it looks nice. It's just a bank, a collection of balances of a user. So do we really need to think about this synchronization? I think that's my understanding of the problem. I think that this is not really correct to make all objects thread safe. I would even say that this is the right way, is to make them all not thread safe, and then introduce decorators which will make them thread safe when necessary. So here the bank object is not thread safe. We create another save bank, which is which encapsulates the original bank. And then does this. So now we have 2 banks. The first one is not thread safe. If you use it directly in your multi-threading environment, you're going to have problems. You may have problems. If you want to get a guarantee, and then we put the documentation here, this class is thread safe. So we have 2 parts of the documentation. This one says it is thread safe. This one says it's not thread safe. And now it's up to you as a programmer to decide which one do you going to use, which one is more, which one do you need. Now it's up to you. It's the decision is in your hands. If you want to just a bank in one thread, you just a bank. If you want it set safe, you say save bank. You decorate it. Of course you need to create an interface. You need to make it nicer. This is just a really a draft. So you need to make them implement the same interface. I would call this one default bank. This one going to be save bank. They will both implement interface bank. So it'll be way nicer. But you see the point here. So I decorate it with the save bank, I run it again, and it will work fine. So you see, with the decorator, it's going to be no errors. If I remove the decorator and run it again, there will be errors. But the decision is mine. So I decide, what do I want to do? If I want my code to be thread safe, I create a decorator, it becomes thread safe. What's wrong with this approach? Why? I mean, I published an article about that on the blog a few months ago, maybe even like a year ago, and I suggested that, and I said that in general, the general practice, the good practice would be to make all objects non-thread safe and supply and provide synchronized decorators for all of them. So if you create a bank, supply a synchronized decorator, this one, for your bank. If you create another object, like we do in Cactus, look at the Cactus library. Now look at the left of the screen. Now let me take my face here. Yeah, so if you look at the code, for example, we create, we have, for anything actually, we have a list and we have sync list. So sync list is a synchronized list. It encapsulates a list, and it is a list, but it behaves in a synchronized way. Well, we're using this primitive from JDK. If it's input output, we have input and we have synchronized input. There you go, which is using the word synchronized. So by default, by definition, the input is not thread safe. But the sync input, oops, you see it says there is no thread safety guarantee. This is wrong. Thread safe input, there is no thread safety guarantee. That's a bug. This class is thread safe. That's how the documentation should sound. And we have it for everything. So for each primitive we have, for each class we provide, we have a synchronized decorator which helps you to make it thread safe. The only problem with that is performance. So some people say, and you can read the comments on the blog, they say that it's going to be slow in some situations. In most cases it's going to be okay. In most cases just this synchronized word will be fine. But sometimes you may implement thread safety differently, in a better way, because there are better ways. For example, you know, it's a very classic example that the hash map, we have hash map and we have concurrent hash map, which is a synchronized version of hash map, but it works faster than just this synchronized primitive from JDK called synchronized map. So why it works faster? Because they implemented the specific algorithm there which knows how to deal with multi-threading and without the use of the synchronized keyword. Because like I said, the synchronized keyword is locking all the threads. It's not really effective way. It actually turns your multi-threading situation into single threading situation. So there, like here, there were like 1,000 threads coming in, and then we just lock them one by one and we put them in one line. So finally, in the end, they will go one by one, not in parallel. We're going to use just one CPU. It will just execute each piece of instructions after another piece of instructions. They will stay in one single long line of instructions instead of going in parallel. Because we cannot do it. We cannot allow them to touch our balances from multiple points. We need to put them in line. But it's not effective. Of course, it's slow. It may be slow. It will be slow. It's the slowest option, actually. So this synchronized keyword, it's the slowest option you can ever have. But it is safe. It's going to be, give you a guarantee 100% in all situations. But it's the slowest option. If you need something faster, in that case, you may want to implement thread safety algorithm right inside your bank. For example, look at this. Here we lock the entire bank with this safe bank. So we actually, this code we have right now, it is similar to this one. See, we lock too much. That's what we do. We lock this line, and even the last line. We don't want to lock that. We already found that because it's just reading the data. We can easily move it here, but we don't do it. So we put too much in the same line. We sequentialize too much. If we would be able to create safe bank inside, I would do it a little bit better. First of all, I would move that line outside. Second, I would say here, instead of hash map, I would use concurrent hash map, which is a hash map which is thread safe inside. I would remove that, and I would make it safe bank. If the performance would be the primary requirement, if that would be super important, I would say this class is thread safe. I would call it safe bank. I would remove the synchronized word at all, and yeah, let's compare the performance, to prove my point. So this class is not thread safe. Well, this one is thread safe, but with the synchronized keyword. That's the old version, right? That's how it would work if we would use the save bank. That would be hash map like it was before. Here, here, here. Okay. So they are now both thread safe, but this one would be bank 1 and then going to be bank 2. But here I would do it differently. I would say concurrent hash map, I would say put if absent, and then I would say this balances compute This is Java 8, so I'm using some stuff from Java 8. Compute, let's check the documentation. Key, value. I've never used it, but I believe this is what we need. Do I need this? Compute if absent. So this is coming from, I believe we need to do return I guess it's this way. Return V plus dollars. I guess that's what we need. Let's check. I'm not sure 100%. Again, I said I never used that one, but let's see. Let's first run them both and see that they actually work. Okay, let's run bank 1. Let's run bank 2 first, which we had before. So bank 2 is the one. Let me move my face left again. So bank 1 is what we had before. Bank 2, sorry. Let's place it in the right place. So bank 1 is what I had before. We were using it before. Bank 2 is my new version, which is also thread safe, but without the synchronized word. The first one should work. It will do 1,000 increments, but it will do it one by one. It will do them. Works fine. Let's try bank 2. It is supposed to do exactly the same, and it should return the same number, I guess. Let's see if it works. It works. But now let's compare the time it takes for the first execution and the second execution. We say it's going to be milliseconds. You follow, right? So I'm just I just want to see how long it takes for. Okay, let's calculate the bank number 1 and see how many milliseconds takes to increment 1,000 times the same bank for the same user. It says 900 milliseconds, so it's almost a second. Okay, and now bank 2, which is not using the word synchronized, it's using the internal concurrent hash map, which is doing it in a special algorithm, but without the synchronized keyword. So now the Java machine will use all CPUs, all I have, the 8 of them, or I think I have 8. So it will use all of them, and in parallel we'll try to increment it in a more effective way. Let's take a look how much more effective it will be. You see, it's almost twice faster than with the synchronized keyword. It's a big gain of performance if you need it. That's my point. So if you need it, then you do this way. Then you try to implement, then you try to make your object thread safe by definition. If you don't need it, I would recommend in most situations, in the majority of cases, you just provide your code like this. You say, my code is not thread safe, but here's a decorator for you, a synchronized decorator. Use it, it will make the code thread safe. If there is some very special need for performance, then in that situation you need to go for, you need to go deeper and implement it in some special way so it will be faster and thread safe. I believe that you will not see that performance problems in most cases. In most cases you will be just fine with synchronized decorators because the code will be cleaner, because this code cares nothing about synchronization. Of course this code is also looks good, but this is because of this primitive example. This one is quite procedural but really easy to read, easy to understand what's going on. This one is more more low level, and it uses some, you may argue that this one also looks good. I agree. But in general, I would say that extra synchronization, any thread safety makes code more complex somehow, makes code more difficult to read. And readability, like I said many times, readability is way more important than performance in the majority of cases. Not in all cases, of course. Sometimes performance is more important. But in most cases, it's better to make the code easy to read, easy to understand, and then provide decorators for thread safety, instead of making the internals of the object more complex. That's what I wanted to say. We don't have time for questions now, but I think I gave all the information I wanted to give. And there are not so many questions in the chat, so I guess everybody just, they just, just flaming about my face, I guess. All right. Yeah, that's my point. Thank you very much. Thanks for coming. Thanks for listening. There were 30 people today. It's quite good. See you next month. Like usually, the first Wednesday of the month, 11 in the morning, Pacific time. Bye-bye. Thanks for being with me.